Hey guys, welcome back to another calculus video. This is section 2.4, infinite limits. And so we're just going to give you a brief overview here, and then I'm going to show you the couple of things that I expect you to be able to do for this section. We're not going to get into full detail for this section. I'll show you the stuff that I'm interested in you being able to understand. Okay, so the idea of an infinite limit is this. First of all, if I say infinite limit, technically the limit doesn't exist. For a limit to exist, it has to equal a value, right? But infinite limits mean that it doesn't exist in a special way, okay? And so the idea is this, that as you approach a value, as x approaches, in this case, -1, as x approaches -1, from the left-hand side, what's happening to your y values? They're going up, 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 without bound. This is a vertical asymptote here at x equal -1. And so they're going up, up, up without bound. We represent going up without bound as infinity. Okay. How about from the right-hand side, as x approaches -1 from the right-hand side? Again, the function goes up, 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 up. And so it's going positive without bound. That's positive infinity. So just like always, that means that if you have the limit from the left and the limit from the right as the exact same, then the limit is that, positive infinity. And so again, when we write the limit's positive infinity, that does not mean the limit exists. It simply means that it is unbounded in the same direction. Right here, as we approach 2 from the left-hand side, we go to negative infinity, but as we approach it from the right-hand side, we go to positive infinity. So here we would say that the limit from the left is negative infinity and the limit from the right is positive infinity. And so therefore, if we ask for what the limit as x approaches 2 of f of x was, we would once again put does not exist because they're not going in the same direction. All right, one's to negative infinity, one's to positive infinity, so therefore the limit does not exist at all. To get a second example of this, this is example 1 numerically, so this is example 2 technically for us. To evaluate each of these limits, the limit as x approaches 0 from the right, from the left, and overall for 1 over x. Okay. This time we're going to take some numbers and plug them in. So if we plug in x approaching 0 from the left, -0.1, -0.01, etc., that would be this limit right here that we're looking for. If you plug those in, you see the values of 1 over x. They're getting larger in the negative direction. So this is looking at the limit as x approaches 0 from the left for your function. And this is clearly going to negative infinity. Whereas if we go from the right, as you approach it from the right, you can see that 1 over x is getting larger positively this time, and so we would say the limit as x approaches 0 from the right of 1 over x equals positive infinity. And so once again, what does that mean? This limit, we say this limit does not exist. Okay? So, how do I want you to approach this? This is the way that I want you to approach things from an analytic standpoint. If you have a graph or you have numbers, that's great, but I don't want you just making a table of values. We still need to think of this analytically. So from that standpoint, what does this look like? For looking for one-sided limits, if you plug in for a and you get a non-zero number over 0. Now remember, if you get 0 over 0, that means nothing. It doesn't mean infinity. It doesn't mean 1. It doesn't mean anything. You have to do some more work. And there's some of you that are getting stuck with that. If you get 0 over 0, that does not equal 0. Okay, you've got to do more algebraically and simplify and figure it out. However, if you get 4 over 0, 7 over 0, -3 over 0, then you know it's going to be, again, one-sided wise anyway, it's going to be plus or minus infinity. So all you need to do is determine the sign. So let me show you what I mean by that. Take the limit as x goes to 7 from the left of 5 over x minus 7. So we plug it in. Plug in 7. And you get 5 over 0. Okay, so that tells me I'm going to get plus or minus infinity. Now the question is which one? How do I determine it? Well, there's two ways to do it. First way is to try a couple values really close to the left-hand side of 7, so 6.9, 6.99. And here I'm not worried about, the only reason I'm allowing you to plug in numbers at this point is because you've already verified I've got an infinite limit. As soon as you see this, you know you have an infinite limit. And so once you know that, then you can plug in a few numbers. But you can't just plug in a few numbers. Okay? You have to verify it first by getting a non-zero over 0. So if we try 6.9 and 6.99, we end up with, plug in 6.9, you get negative 50. You plug in 6.99, you get negative 500. And certainly those are not very big numbers comparatively, but we already know we're going to infinity. So now we just can say, okay, therefore the limit as x goes to 7 from the left of 5 over x minus 7 is equal to negative infinity. Okay? You can say that. The other way you can do it is just look at the signs. So if I'm taking the limit as x goes to 7 from the left, 5 is 5, it's always positive, right? If I'm plugging in numbers that are less than 7, to the left of 7, less than 7, then x minus 7 is always going to be what? Negative. So a positive divided by a negative is always going to give you a negative answer, and therefore I know it's negative infinity. Again, you can only do this once you do this first. This is the first step. If you suspect that you're going to get an infinite limit, you need to show me that it is indeed a non-zero number over 0. Then you can use that fact to justify plugging in a couple of numbers or just checking the signs. Okay, that's the way I want you to do it. Okay, so now you try this one. You try this one. And then pause the video and I'll come back and show you the notation you need. Okay, so what do we do? First things first, plug it in. You get 5 plus 5 over 5 squared minus 25, you get 10 over 0. That right there tells me infinite limit, plus or minus infinity. So now the question is which one? And so if you want to check it out, which one now? You could have factored this and simplified, but you'd still get the same thing. You'd still get a 0 on the bottom, so it doesn't matter here. So that's why we usually plug it in first. So if you're plugging in numbers bigger than 5, 5 plus 5 is positive. If you're plugging in numbers bigger than 5, then 5 squared is bigger than 25, so that's going to be positive. You're going to get positive infinity. And you don't need to write the plus, okay? I know it's plus, but just to emphasize it, right? So the answer here then is infinity. And that's it. Simple enough. Okay? Now, what does this give us? We remember the first graph that we looked at? We demonstrated infinite limits by looking at these asymptotic behaviors. Well, it turns out that that is always the case for infinite limits in our definition. The function f will have a vertical asymptote at x equal a if we have the following limits at a. The limit as x approaches a from the left, plus or minus infinity, from the right, plus or minus infinity, or the whole limit, plus or minus infinity. Notice that it only requires one of the above limits for a function to have a vertical asymptote. Okay. So, how do I determine vertical asymptotes? Well, what do I know? I know that I'm going to get an infinite limit if the denominator equals 0 and the top doesn't. So, I set the denominator equal to 0. First step, set the whole denominator equal to 0. I get x plus 3x minus 3 equal to 0. And so I get x equals plus or minus 3. That's not my answer. Those are the candidates. This is who I need to test. Okay, so now I do the test. First thing, limit as x approaches 3, do from one side, doesn't matter, from the right, say, of f of x. Okay, so if I plug in this number, I get 6 over 0. That means plus or minus infinity. Which one? Guess what? It doesn't matter. If you were in the classroom, I'd be covering my mouth right now with both hands to make a megaphone. It doesn't matter. Why not? Because either one gives you a vertical asymptote. Either one. It doesn't matter. So I can stop right there And this is enough to say vertical asymptote at x equal 3. Boom, done. Now, what about the other guy? The limit as x approaches negative 3. Again, we can come from either side, so let's just pick one. X plus 3 over x squared minus 9. Now, if we plug in negative 3, watch out. We get 0 over 0. Okay, so that means we don't have one. No, that's not what that means. That means you have to do something else. You can never, ever, ever, never, ever stop with 0 over 0. It's called an indeterminate form because it tells you nothing. It gives you no information about the limit whatsoever. It simply says do some more. So what are we going to do? We're going to factor the denominator, of course, and get an x plus 3 on the top, get an x plus 3x minus 3 on the bottom, divide a 1 up top, and get 1 over negative 3 minus 3, so we get negative 1 over 6. That's not infinity, so that means that there is a vertical asymptote at x equal 3, but not at negative 3. Okay, and so I don't have to say not at negative 3, but I do have to test this. Without this stuff, you've left somebody out. Okay, so I need to see either that the limit is a non-zero number over 0, so that's infinite, or I need to see a value. 0 over 0 tells me nothing. Okay, so be careful with that. So those are the two processes. There's a significant number of problems to play around with, both in my math lab and in the worksheets. You're going to need to do all of them because there's a lot of work to be done here, practice-wise, because this is one of the more, I guess, theoretical or slightly more challenging concepts to grasp. And so the basic idea of running off to infinity is not a big deal, but how you notate it algebraically is a little bit more challenging. Okay, so make sure that you go through a lot of those problems, always available for questions if you have them. And there you go. Thanks.